Καλησπέρα σε όλους και από εμένα. Ελπίζω να φαίνομαι και να ακούγομαι. Μετά την πολύ ενδιαφέρουσα παρουσίαση του Απόλλωνα με πιο συστημικό περιεχόμενο, θα γυρίσουμε πάλι σε λίγο πιο δικτυακά πράγματα. Απόλλωνα, αν δεν κάνω λάθος, σε βλέπω στο βίντεο. Πολύ ωραία, ευχαριστώ πολύ. Και μετά από αυτό το μικρό διάλειμμα στα ελληνικά, vGRNOG είμαστε, πρέπει να ακούγεται και η γλώσσα μας οπωσδήποτε. Μου επιτρέπετε να γυρίσω πάλι στα αγγλικά για να υποδεχτώ έναν εκλεκτό καλεσμένο από τη Juniper. So I'm switching to English. It is with great honor that we will have a presentation from Julian Lucek, a distinguished systems engineer from Juniper. And he will be talking about recent developments or latest developments in segment routing, which is an area that has gained a lot of attention recently in service provider networks. Julian, the floor is yours. Thank you very much for coming.
Thank you very much, Kostas. So yes, I'm going to talk about FlexAlgo and BGP Classful transport. Before I go on to those topics in detail, I'll just give a sort of overview of the segment routing landscape. So, as you probably know, segment routing has now been around for 8 years now. You know, the first IETF drafts were all the way back in 2013. And so over time, quite a lot of different aspects have been added to segment routing. And this diagram, you know, sort of summarizes that. And there are two major branches. And so if you look at this branch on the right-hand side, traffic engineering, then there are two ways of achieving it. One is distributed traffic engineering, where you configure the requirements on the ingress router, and the ingress router does the path computation. On the other hand, central controllers have become very popular. And so with those, you can do more advanced traffic engineering use cases related to self-driving networks. Things like automated congestion avoidance, where the controller, if it sees through telemetry that links become congested, it can move traffic engineered NSPs onto different paths. Network self-healing in a similar vein when errors are detected on a particular network element, and also using segment routing PSIDs, egress peering engineering, where you're controlling the way traffic flows out of your network towards your eBGP peers. And then the other branch is shortest path routing, and within that, one of the things I'm going to talk about today is FlexAlgo, which allows you to have multiple IGP topologies, if you like, called FlexAlgos, overlaid on the same physical infrastructure. So that would be quite a large topic for today. And then also in this corner, bottom left, you can see we have fast convergence in the shape of topology independent LFAs. And so that allows you to have fast convergence, whether you're doing shortest path routing or the traffic engineering, in fact. And then the BGP Classful transport, which was part of the title of this talk, isn't on this diagram, because BGP Classful transport isn't a subset of segment routing, but it can use segment routing as the transport within one or more of the domains where the BGP Classful transport is being used as the glue in between the domains. But we'll see how that works later on. So with that, let's now talk about the FlexAlgo in itself. And I'll start off with this example. And so, as I mentioned, FlexAlgo allows you to have multiple IGP topologies within the same physical network. And with a normal IGP, as you know, you have SPF calculations, which determine, you know, what's the shortest path neighbor from the point of view of me, a node in the network, towards the destination of this packet. And the same thing happens within FlexAlgo. And so if you have multiple FlexAlgos in a network, you have separate SPF calculations, you know, one set of calculations for each FlexAlgo. So this example actually has, you know, the normal IGP topology, which I call the gray topology, and all of the nodes are members of it. But then also we have the blue FlexAlgo, and so the nodes at the top of the slide are members of the blue FlexAlgo, while the nodes towards the bottom of the diagram are members of the red FlexAlgo. And in this example, let's assume that the metrics on all of the links are equal, let's say 10 by way of example. Now with segment routing, even if you're not using FlexAlgo, each node can be configured to announce a SID. In effect, that is a label to reach that particular node using the shortest IGP path. And so the normal IGP I mentioned, every node is a member of it. And so PE3 will have a SID associated with its loopback address as a result of its membership of that normal IGP topology. And in the example, that SID value is 3003. Now, on the other hand, I mentioned that PE3 is a member of the blue FlexAlgo, and so it will have a different SID value of 1003 in the example. And both of those SIDs are associated with its loopback address. Now, in contrast, PE4, it's a member of the red topology, the red FlexAlgo, and so it has a SID associated with that, 2004, and also a SID, a different value, 3004, associated with its membership of the default IGP, which I've called the grey topology. Now, this information, all of the nodes knows which nodes are members of which FlexAlgo, because that information is flooded via the IGP, ISIS, or OSPF. And as I mentioned, each node does its SPF computations separately in the scope of each of those topologies. So for example, PE1 will do one set of SPF calculations for the fact that it's a member of the default IGP topology, and a separate set of calculations because it's a member of the blue FlexAlgo. Now, let's have a look at an example of using the grey topology. So suppose PE1 wants to send traffic to PE3, just using the normal grey topology. I mentioned that the link metrics are all equal. And so when PE1 did its last SPF run, it would have determined that its shortest path neighbors to PE3 are both P1 and P2. It's got two ECMP, next hop neighbors, P1 and P2. And so it ECMPs the traffic across those two neighbors. And to make the traffic use the grey topology in order to reach PE3, it uses the SID value of 3003. So that's the value of the MPLS label that it puts onto the packet. Now, when the packet reaches P1, from its point of view, it's got two shortest path neighbors towards PE3 in the scope of the grey topology. So it ECMPs the traffic across both PE3 and P4, as does P2 for the same reason. And so you can see the traffic reaches PE3 over these various ECMP paths within the scope of this grey topology. So that's perhaps for vanilla traffic, let's say. Now, suppose in contrast, PE1 needs to send some other traffic to PE3, and that traffic we want to be confined only to the blue topology. Now, when PE1 did its last SPF run in the scope of the blue topology, it knew that its shortest path neighbor towards PE3 is only P1, because P2 is not a valid neighbor in the scope of the blue FlexAlgo, because P2 is not a member of that FlexAlgo, and PE1 knows that. And so in fact, it's only got one shortest path neighbor in the example, which is P1. Likewise, P1 has only got P3 as its shortest path neighbor towards PE3, and P3 has PE3 because that's the destination. And so at the end of the day, the packet follows the path as shown by those blue arrows. And in order to ensure that PE1 only uses the blue FlexAlgo, to ensure that it's actually confined to that FlexAlgo and can't exit it, it puts onto the packet the MPLS label 1003, because that was the SID associated with PE3's membership of the blue FlexAlgo. And in a similar vein, PE2 wanting to send traffic to PE4 only using the red FlexAlgo, it's determined that its shortest path neighbor is only P2, and furthermore it knows to put the label value 2004 because that's the SID associated with PE4's membership of the red FlexAlgo. And in fact, this slide illustrates one of the early applications of FlexAlgo, because the original operator who had this use case wanted to have particular special traffic obey path diversity constraints. So it wanted to send one flow that could only flow along the blue plane, and a counterpart flow, which was actually carrying identical traffic, only following the red plane, to give a sort of live operation for the ultimate in resilience, in the knowledge that a packet would never jump from one plane to another. And so the FlexAlgo gives you a very convenient way of doing it, just by giving you a sort of constrained IGP topology as determined by the FlexAlgo membership, as you can see. So that's one example, but now we can look at a different example. So here, the physical topology is shown in grey, and you've got these various P routers and PEs. And then you've got the red FlexAlgo at the bottom left of the slide. And you can see that you can decide which nodes are going to be members of it, and indeed which members links are going to be part of it. And so you can see, compared to the physical topology, you know, P5 is not a member of that red topology, and some of these cross links, none of these diagonal links are members of that red topology either. In contrast, the blue FlexAlgo, it's got you know, some of the nodes in common with the red FlexAlgo, but also some of them are different, like PE4 is not a member of the blue FlexAlgo, for example. And so in general, you could have multiple FlexAlgos, and a given link or a node might be a member of, you know, perhaps just one of them, or several of them as needed by your particular use case. So now we can look at another example of how we can use FlexAlgo. And this is a situation where you've got different types of traffic that have different requirements in terms of the type of metric that you want to use for the IGP calculations, the SPF calculations that happen within the scope of the default IGP, or within the scope of a particular FlexAlgo. And sometimes you see a situation where, especially if somebody's got a global network, they might be carrying multiple services. They might be carrying bulk internet traffic on the one hand, and delay sensitive business VPN traffic on the other hand. And a classic situation is, if you're sending traffic from Europe to Asia, then the lowest latency path is directly eastwards around the globe, but that's also very expensive in terms of cost. And so you only want to send your latency sensitive business VPN traffic, you know, directly eastwards around the globe. On the other hand, if you're sending bulk internet traffic from Europe to Asia, you probably want to use transatlantic links and then across North America and trans-Pacific links, because although that's a much greater latency path, the cost is quite a lot cheaper. And so overall, you want to treat these two different traffics in a different way. And so you can achieve that using FlexAlgo. And so in this diagram, the thickness of the links is according to you know, the bandwidth of these links. So you've got higher bandwidth links along these diagonals than you have along these horizontal or vertical rails within the core of the network. And in the example, the bulk internet traffic, which needs to follow the, you know, highest bandwidth paths preferentially, that is using the default IGP, and it's using the metrics that are shown in blue on each of those links. And so, for example, if traffic's going from P1 to P2, in the scope of this blue topology, it's going to go via P5, which is what we want for the internet traffic. On the other hand, the low latency traffic, the business VPN traffic, is mapped onto the red FlexAlgo, and the red FlexAlgo is using metrics as shown in red on each link. And so traffic going from P1 to P2, we want to go straight across from P1 to P2, which is the lower latency path. And you know, this different metric setup will ensure that. And so overall, you have a situation like this, where traffic going from PE1 to PE3, which might be on, you know, opposite sides of the world, the bulk internet traffic following the normal IGP shortest path is going via P5, while the delay sensitive business traffic, which is using the red FlexAlgo, is going direct between P1 and P2. And so, as you can see, using FlexAlgo, we've got the flexibility to have different metric setups on the network and different types of traffic, you know, using a different topology in terms of the metric regime that they're subjected to. How you set this up, now, what you do is, in the IGP, you know, ISS or OSPF, you configure the normal IGP metric as per normal, on each interface. But then in addition, you also set up a delay metric, and that delay metric can either be static, or in fact it can be a dynamic one, which is automatically derived from live TWAMP probe packet measurements, and that feeds into the value of that delay metric. And then for that red FlexAlgo that we talked about in the previous slides example, what you'd do is configure the FlexAlgo to actually use that delay metric. And so you'd say metric type delay metric. Generally speaking, you've got a choice of 3 different metrics that you can use for a given FlexAlgo. You can have normal IGP metric, or the TE metric, or the delay metric. So that gives you, quite a lot of degree of freedom to have different metric regimes for different FlexAlgos, compared to the normal IGP. So that's, a sort of overview of how FlexAlgo is working. What I'd like to talk about now is how do we map traffic to a given FlexAlgo, because I've been talking about, oh, this traffic uses the red FlexAlgo and this other traffic uses the blue FlexAlgo, but so far I haven't said how we actually do that mapping. And so this is how we do it. There's a thing called colors. So colors provide a convenient way to actually auto-map prefixes, which might be plain IP or might be VPN prefixes, to a particular transport. That transport could be a particular FlexAlgo, or more generally speaking, could be a particular TE tunnel, could be an SRTE tunnel or RSVP TE tunnel. And these colors are a very versatile approach, and in fact they play an important part in BGP Classful transport, which I'll be talking about later on in this session. So let's see in a little more detail how it's working. And so in this example, we've got PEX on the left, we've got PEY on the right, and then we've got a core network with routers which aren't shown in the diagram. And what is happening is that PEY is advertising various prefixes to PEX via BGP, could be plain internet, could be EVPN, could be layer 3 VPN. And in this example, PEY has advertised 10.1 and 10.2/16 with a color community attached. So this color community in the example has value 100 for these prefixes. And what that triggers PEX to do is to map the traffic onto the transport that has that corresponding color. And the red FlexAlgo has been configured to use color 100. And so it's just a match. Prefixes with color community 100 are mapped automatically onto the transport that has color 100 associated with it. In contrast, PEX is also received from PEY 11.1, 11.2/16, but those have color community 200. And so for that, PEX chooses the blue FlexAlgo because that has color 200 configured as being associated with it. The example is showing FlexAlgo, but equally these could be SRTE tunnels with particular colors, different color on each tunnel, or RSVP TE tunnels as well. So the color is a generic mechanism of mapping traffic to different types of transport, whether it be FlexAlgos or different types of TE tunnel. That was a sort of introductory example. Let's have a look at some more sort of involved example. So this is related to actually being able to have coupling between the world of telco cloud and the transport network, where on the left-hand side and the right-hand side of the slide, you've got 2 data centers. It might be in a mobile network where you've got an edge data center on the right and the regional data center on the left. And then within these compute resources, you've got workloads. They might be RUs and DUs, for example, in a 5G setup. And those are separated into different virtual overlay networks. You could regard these as slices, in fact. And let's suppose in this network that traffic from the green and purple overlay networks or slices need minimum cost transport when they travel across this transport network. Well, traffic from the yellow overlay network just needs minimum cost transport. And so we need to ensure that they pick up the right flavor of transport when they reach these DC gateways. And the way we ensure that is by having the prefixes, which are typically layer 3 VPN prefixes, corresponding to these compute resources, we ensure that those are advertised with a color community, which is normally done by this SDN controller that's in charge of the cloud overlay networking. And so it will be adding color communities to the prefixes. Those percolate across the network to the DC gateways. And so that triggers the DC gateway to put this green and purple traffic belonging to the corresponding overlay networks, because they wanted minimum cost transport, onto this blue transport, which might be a blue FlexAlgo, while traffic from this yellow overlay network goes on to the red transport, because that has the corresponding color. So that's how it works at high level. What we can do now is to look at it in a bit more detail shortly. The other thing I'll point out is that within the data centers, we're not attempting to extend this transport through the data centers, because normally in the data centers, people just want to use IP because they want to use ECMP across a symmetrical spine and leaf. And so what you have to transport the layer 3 VPN labeled packets to the compute resources is MPLS over UDP tunnels to span this IP only infrastructure within the data center. So even though this colored transport doesn't even touch the compute resources, the controller can dictate what type of transport is used by its workloads by virtue of the color communities that it attaches. And so we can look at a more detailed diagram just to illustrate it more concretely. And so we're looking at a cross section through that same network, and we're focusing on the green overlay network. And what happens is that the SDN controller installs a virtual router on each compute resource, which is a bit like a PE, because it's doing layer 3 VPN. It has a separate VRF for each of these overlay networks, for each of these slices. And focusing on the green one, we've got these two compute resources, CNF2, CNF4, attached to this green VRF within this server. And what is happening is that prefixes pertaining to these compute resources are advertised via BGP by the SDN controller, first of all, to the local DC gateway. And so what we can do is look at what this looks like. And so you've got the prefix, let's say CNF2, layer 3 VPN label V2. You've got a route targets associated with that VPN, but also very importantly, this color community, which has a value of 200 in the example. DC gateway receives it, changes next hop to self, advertises it to the other DC gateways. This changes next hop to self, and then advertises it to the local SDN controller, and then finally it ends up in the green VRF on this vRouter on the compute resource in this DC here on the left-hand side. Now, what happens in the forwarding plane? So let's suppose CNF1 sends a packet whose destination IP address is CNF2. It arrives in the green VRF, and there's a route as shown by this BGP setup here, which says that from the point of view of this vRouter 1, the BGP next stop is this local DC gateway 1. The VPN label at this point is V2 double prime. And so this triggers the vRouter to put the packet onto the MPLS over UDP tunnel with the VPN label V2 double prime in order to reach the DC gateway. On reaching the DC gateway, the packet will be launched onto the appropriate colored transport. So this color community that was advertised from this DC on the right-hand side dictates the fact that this red path will be picked up, the one with color 200. This could be a FlexAlgo, could be a traffic engineered LSP. And so the packet is put into that MPLS transport across this transport network. So this L1 represents the label on one of the hops for that transport path. Packet arrives at DC gateway 2, and this V2 prime VPN label is exposed, which triggers DC gateway 2 to put the packet onto the MPLS over UDP tunnel that terminates at vRouter 2, and from there it goes into the green VRF into CVNF2. So overall, what you can see is that by virtue of this color community that was advertised from the cloud overlay, we've controlled what flavor of transport is used within the underlay, within the transport network at the heart of the network. And so you can see you've got this coupling just by virtue of this color community and this color mapping scheme, which I've been describing. So with that, I think we can go on to the final section of the talk, which is to talk about BGP classful transport. And what this is doing is extending this color mapping paradigm across multiple domains. These could be across multiple ASs, for example, because the examples so far are all within one domain, in fact. And the scheme is such that you do not need to expose the internal topology of a domain to any other domain. And so each domain can make its own choice of what transport technology it's using. So one might be using FlexAlgo, another one SRTE, another one RSVPT, for example. But in any case, whatever you make those choices to be, BGP Classful transport is acting as the glue between those domains. And BGP Classful transport is very similar to BGP labeled unicast, which lots of people use. The difference is that BGP labeled unicast just says, okay, for this PE, for this loopback address of this PE, here's the MPLS label that's associated with it, and it's just one label. Well, in the BGP Classful transport, you've got color granularity, and so you can have color awareness for these BGP labels. And so for each color that a PE is involved with, there'll be a different label value associated with it. And like before, the color denotes the flavor of the transport, like is it minimum latency, is it cheapest monetary cost, and so on. So we can look at an example here. And so what we've got in this slide, we've got PE1 on the left-hand side, we've got PE2 on the right-hand side, and then we've got 3 ASs, AS1 on the left, AS2 in the middle, AS3 on the right-hand side. And associated with PE2's loopback address, 10.0.0.1, because in this network we've got two different colors involved, color 100 and color 200, PE2 will be advertising two different label values associated with that loopback address, one corresponding to color 100, the other corresponding to color 200. And those will percolate across the network as shown by those dotted green arrows. From ASBR to ASBR, perhaps via route reflectors within each domain. ASBRs, would be changing next hop to self typically. And so at the end of the day, PE1 has got that advertisement, two colors associated with PE2's loopback address and corresponding labels for each. Also, PE2 will be advertising service level prefixes. This might be just plain IP prefixes, might be VPN prefixes, and those will have color communities to control what colored transport is used by that given prefix. And so PE1, looking at the prefix, might see, okay, it's got color community 200, so I need to use the color 200 transport. And what it does is, first of all, it puts on the VPN label on the packet, if it's a VPN packet, and then it puts on the BGP-CT label, the one corresponding to color 200 for the destination, PE2. And then, because the BGP next hop at this point is ASBR1, it identifies what is the local transport to reach ASBR1, which is color 200. It might be a blue FlexAlgo, it might be a blue colored, traffic engineered LSP, and the packet gets launched onto that. The packet, when it arrives at ASBR1, will have the BGP-CT label exposed because of penultimate hop popping, and that triggers it to send it to ASBR2. And ASBR2, knowing that that corresponds to color 200, again launches it onto color 200 transport. And similarly, in AS3, ASBR4 will launch it onto color 200 transport. And so, as you can see, this BGP-CT label, because it's got color awareness, because it corresponds to a particular color, is controlling the fact, is determining the fact that each time the packet enters a new domain, it's put onto the correct colored transport. And so in this way, the BGP-CT label is acting as the glue to ensure that we use the right color transport of the appropriate type within each domain. So that's the BGP-CT in a nutshell. So with that, that brings me to the end of the talk. And finally, here's some further reading if you'd like to read into these topics a bit more. Like, first of all, we've got the IETF draft associated with FlexAlgo, the IETF draft associated with BGP-CT. And then finally, if you're interested in this coupling between the telco cloud and the transport layer using this color community binding mechanism, there's a blog on that topic as well. So with that, thank you very much for your attention.
Thank you, Julian. I definitely have a couple of questions for
Sure,
Julian,
sure.
but is there anyone else that has questions I will have to place myself at the end in this case. If there is anyone that has any questions, please raise your hand. Μπορείτε να κάνετε όποια ερώτηση θέλετε και στα ελληνικά και θα τη μεταφέρω εγώ. Okay. We have a question from Dimitris Kalogeras. Wait, I lost him. Δημήτρη, αν θέλεις να κάνεις κάποια ερώτηση. Oh.
Okay. Yes.
Okay.
Okay. So my question is the following. I mean, typically this is the CT the CT functionality terminology. Is it coded inside the labels, or is there any other possibility? Is it a control plane or data plane?
Yeah, yes, good question. Yes, it's both actually, because there are BGP extensions to cater for it. So you know, the draft describes the BGP extensions, you know, used to achieve it, you know, to modify BGP to be able to have this, you know, sort of, it's called classfulness, you know, this sort of color awareness, and, you know, different label values corresponding to the same destination routes are each corresponding to different colors. So definitely there's, you know, BGP extensions, you know, associated with that. And then it does have a bearing on the forwarding plane, the data plane, in that, you know, you'll have a different label which has come from BGP-CT, you know, within the packet stack, which denotes well, it denotes two things in one, actually. That, you know, particular BGP-CT label value, let's call it L1, will both be saying, you know, what the destination PE is of that packet, and furthermore, what colored transport should be used to reach that destination PE. And so in that example that we looked at, let's say it's a VPN label, you know, it's a VPN packet. PE1 will typically end up putting a 3 label stack. Well, it could be more actually. I mean, well, first of all, the bottom label will be the VPN label, and then the next label above that, the label second from bottom, will be the BGP-CT label, and then there'll be one or more labels corresponding to the transport. You know, like if it's FlexAlgo, it would just be one label, you know, which is the node SID of ASBR1, or it might be SRTE LSP, which might be a label stack. But you know, certainly in the data plane, you've got this BGP-CT label as well.
What is the reason that you don't use, for instance, flow specs for the control plane signaling or terminology? Is it because this is kind of per AES terminology stuff, or something different?
I would say, I think this is a sort of natural extension to, you know, BGP labeled unicast, because if you ignore the colors, like say if it was just one sort of transport, you know, one label for this PE2's loopback address, that would be, you know, sort of the way that BGP labeled unicast has been used, you know, for example, in Seamless MPLS deployments. And so this is very similar in spirit. It's sort of, you know, it's very similar to the BGP-LU paradigm, except that you've got this color awareness now, and, you know, multiple labels as a consequence corresponding to any destination PE, you know, a different label for each color. So it seemed like a natural way of doing it. And you know, also it sort of, you know, percolates across the ASs in a, you know, same sort of way, same sort of situation where the ASBRs are doing next hop self and things like that. So it's, in that sense, it's a sort of natural extension to the BGP LU, in fact.
Okay. Thank you.
There is an extra question from Blake Willis. Blake,
Oh, hi, Blake.
let me pass you the mic.
It's not staying unmuted. Thanks for the talk, Julian. My question was, given now that we have FlexAlgo and BGP-CT, how far do you think one can get without an MPLS data plane? Like, what use cases do you think still really require end-to-end MPLS? I mean, obviously, if you need like auto bandwidth and stuff, you're still going to need it. But
yeah, I mean, this, you know, I mean, you could do it, you know, using SRv6 instead, of course. but you know, I think, you know, this MPLS data plane does the job well, you know, so
I
I
agree
think it'll be the
completely.
predominant one used, I would say. So you know, like you know, we've got some upcoming deployments of, you know, FlexAlgo, and you know, they are going to use the MPLS you know, data plane. In fact, you know, similarly for the you know, BGPCT actually. So I think it's here to stay, you know, for the foreseeable future.
Yeah, absolutely,
Definitely.
absolutely.
Yeah.
It's. I guess I should probably turn that question around and ask, you know, what does this enable doing over just like the public internet that one couldn't do before, right? I mean, already SRM6 enables a bunch of that, but this kind of takes it quite a bit further.
Oh, you mean doing this over the public internet?
Yeah, for
right,
example.
right. Yeah. Oh, you mean if there is like the internet somewhere in the middle, like,
Sure.
which is probably color unaware. Yeah. I mean, you can do things like, you know, tunneling in UDP, like there's, you know, for example, segment routing, there's SR over UDP tunnels, and that's quite good if you've got a domain, or, you know, several domains in general, which, you know, don't support labeled transport. You know, maybe, you know, the domain is the internet, like you say. Like, I mean, what you could have is something like, you know, the middle AS, you know, doesn't support, you know, it's just the internet, and then you can have labeled transport in these ASs. I'm just reusing this diagram,
Sure.
AS1 and AS3, and you have this SR over UDP tunnel. So, you know, it's just plain IP packets as far as the internet's concerned, but then when the packet pops out here in AS3, then you can expose the underlying SR label, which controls how the traffic is steered on its subsequent journey within that AS. So you can have these sort of hybrid situations, certainly. Yes, that's right.
Thank you.
Any other questions? Okay, if there is no one left, I guess I will pose my own. Julian, what I wanted to ask is, in your initial slides, you had a brief categorization, let's say, of the traffic engineering. Perfect, yes, I was referring to this slide. So my question, and I guess this is true, could you have FlexAlgo together with traffic engineered LSPs in one network? I mean,
oh, I see.
Could you have this set up? Because, for example, it could be cases, traffic engineered cases, that FlexAlgo cannot handle because it is based solely on SPF computations, even on different topologies.
Right.
So perhaps you might need, generally speaking, FlexAlgo could be good for you, but for some specific cases, you might also need traffic engineered LSPs. So could you have both in the network?
Right. Yeah, you could. I mean, actually, in two different dimensions. I mean, what you could have is this FlexAlgo setup, but then, you know, say within the normal, maybe I'll use this diagram actually. You know, let's say we've got this network, that's the physical network in gray. You've got this red FlexAlgo, this blue FlexAlgo, and what you could do is, you know, completely separately from the FlexAlgo, you could decide to use traffic engineering, you know, for example, in the scope of the gray topology. So you could have a, you know, an SRTE LSP going on a sort of zigzaggy path. You could go PE1, P3, P1, you know, P5, P2, P4, P3, yeah, you know, if perhaps to avoid congestion elsewhere or some reason like that. And, you know, that would be denoted by, you know, maybe a mixture of node SIDs associated with the gray topology, or, you know, maybe some adjacency SIDs as well. Now, in the case of the FlexAlgo, I mean, you could do a sort of traffic engineering in the scope of a FlexAlgo if you're just using the FlexAlgo node SID values. Like in the blue topology, let's say we want to go PE1, P1, you know, P3, P5, P2, P4, P3, you know, sort of more roundabout path using traffic engineering. You could achieve that by putting the you know, node SIDs in that sequence, you know, the node SIDs, the values corresponding to the blue FlexAlgo onto the label stack as launched by P1. So indeed, like you suggested, you can have a mixture actually.
And the final question is, are there actual provider networks that are thinking of deploying FlexAlgo? What is the status in terms of customer demand or deployment without disclosing any?
Yes, sure. Yes,
any
we've
players?
got customers preparing to actually launch it, put it into production. So they're, well on the way to doing that. So some of the use cases I mentioned are, sort of, real world ones that they want to deploy. So indeed,
Excellent.
yes, it's true.
Excellent. Thank you. Thank you once more for your presentation. Julian?
Thank you very much.